You can choose. Okay. I hope people don't get here. We will start. So it is my pleasure to introduce Elazar from Weizmann Institute and then physics. He did his undergraduate and master's in the Technion with Orba and continued to PhD in Stanford with Stevenson and someone else.
PhD was with
Stevenson. Okay, that's what I thought. Okay. And working on high temperature superconductors, actually continuing to this day, graduating in 2009. Did a postdoc in with Denmel and Sastrev, working on quantum many-body systems, topological systems, and in 2012 joined Weizmann Institute, where he's still today, but apart from a brief short detour elsewhere.
What is the joke?
Never mind.
His interests include many-body correlated effects and condensed matter, topological states, high temperature superconductor, 2D materials, twisted graphene, and other correlated quantum correlated systems. And among his honors is Alon Fellowship, Minerva Prize, and the Lavantnik Award for the young scientist in Israel. And today we will hear about the quantum critical methods.
Okay, thanks very much. Thanks for the invitation to speak here. So you'll tell me after 50 minutes, or
yeah, I'll tell you at the party.
Yeah, you don't have to go through all this material. Please ask questions. So I'm going to tell you about something I've been thinking about for several years now, and these are my collaborators on this work. Okay, so the young collaborators are here in the top row. Sam, I started working with him when he was a student at Stanford, and now he's at Berkeley. Yoni, my former student, who's now at Stanford as a postdoc. Xiao Yu was a postdoc with me in Chicago, who's now a postdoc in Florida. This is the younger generation, my student Oli, my postdocs, Johannes and Tobias. These are some of the more senior people I've collaborated with during this journey. Okay, so just to set the background, so what I'll be talking about is critical phenomena. In particular, quantum phase transitions. These are continuous transitions that occur in the ground state of a quantum many-body system. And in insulating states, these kind of transitions are pretty well understood. You can read about them, for instance, in this book by Sachdev. But it turns out that in metallic systems, systems that have a Fermi surface, these kind of phenomena are much less well understood and are still debated today, and that's what we're gonna discuss. Okay, so this is my plan. I'm going to talk about criticality in classical and quantum systems. I'm going to talk about quantum critical Fermi surfaces. Okay, so quantum critical metals, and then I'll show you a little bit of results of numerical experiments that we've been performing on these kind of systems using quantum Monte Carlo, some results, some intermediate conclusions, and some open questions. Okay, then we'll start from a brief introduction to criticality, which I'm sure most of you have seen. And so since this is a lot of this is going to be about criticality, a central theme is scale invariance. And to illustrate scale invariance, I found this nice demonstration online. Some of you maybe have seen it. Okay, so I'm going to show you a simulation. This is a classical Monte Carlo simulation of the 2D Ising model. And I'm just going to show you pictures of snapshots, if it works hopefully, snapshots of the configuration of the spins of the Ising model when the Ising model is tuned exactly to its critical point. Okay? And the challenge is going to be to identify which of these pictures come from which length scale. Okay, these pictures are going to be at different levels of coarse graining. And the question is which comes from which scale. They actually fit into each other. So, okay, so now let's hope this works. Okay, so this is the range of the scales from L equals, yeah. So here are the four pictures. And it kind of looks similar. It's hard to see which is which, but you see that they actually fit into each other in this way. Okay. So this is scale invariance. Okay. The idea is that statistically, the picture looks the same at all length scales. So you can coarse grain more and more. Of course, the pictures are different. They're all random. They're all taken from a random distribution. But this random distribution has the property that it's scale invariant. Okay, it looks the same no matter how much you rescale. And this is a property of a system tuned to a critical point. There's a length scale that diverges, and this is how the system actually acquires this scale invariance. And that has all sorts of nice consequences. Okay, the fact that the microscopic length scale diverges means that the microscopic details of the system are actually washed out. And we get that the long wavelength, long distance properties of the system become universal. They actually forget about the microscopic length scale, and they only depend on things like the dimensionality of the system, the symmetry of the order parameter, and so on. Okay, so this is an emergent type of scale invariance. Okay, our microscopic system had nothing scale invariant about it. It was living on a crystalline lattice that has a certain symmetry, but at long wavelengths, the system forgets about this microscopic scale and acquires this invariance under scaling. Okay, this is actually a small subgroup of a much bigger emergent symmetry of the system, which is called conformal invariants. Okay, so you can not only rescale, but also transform in by any conformal transformation, and the distribution is also invariant under that. Okay, and after many decades of research into these phenomena, there's very good theoretical control using the renormalization group that's really tailored to reveal this kind of scale invariance close to critical points, and backed up by Monte Carlo simulations. Okay, so there really is a huge body of knowledge on these type of critical phenomena.
One clarification.
Yeah.
In a critical phenomena, conformal symmetry need not emerge, right?
That's right. It doesn't always emerge. In this particular example of the Ising model, it does. In many systems, it does, but there are many examples where it doesn't. Actually, in the critical Fermi surfaces that I'll talk about, it doesn't. So yeah, it's very, very common. Okay, so I mentioned universality, and this is really the attractive property of these types of phenomena. You have very different microscopic systems that all display some universal properties like critical exponents, and this is all thanks to this emergent symmetry of scale invariance and the fact that there's a divergent correlation length. And this actually, for theorists, that's very good news as physicists in general. That means that we don't have to understand all the microscopic details of the system to actually be able to make predictions about it. Okay, so this is, in some sense, this is what we seek as condensed matter physicists, and the same concepts of scale invariance, the long correlation lengths, renormalization group, and so on are also important in other fields. For instance, in quantum field theory. Okay, so this is really a very well developed field. Okay, and what I'm going to focus on instead is quantum critical phenomena. Okay, so unlike the critical Ising model, where we tune the transition by tuning temperature, okay, and the transition itself is driven by thermal fluctuations, you can actually get similar phenomena occurring in the ground state of the system at t equals 0. And now the tuning parameter would not be temperature. It would be some parameter in our Hamiltonian. Okay, so imagine tuning pressure in a material, or tuning magnetic field, or tuning material composition. Okay, and the driving force of the transition now would not be thermal fluctuations. It would be quantum fluctuation. Okay, it would be 0-point motion dictated by quantum mechanics. The paradigmatic model that we use to illustrate these types of phenomena is the so-called transverse field Ising model. Okay, if you don't know it, it doesn't really matter what exactly it is. It's some Hamiltonian of interacting spin halves, okay, living on some lattice. And there's a parameter, which is the transverse field, which is used to control the transition. Okay, so what this transverse field does, it controls the amount of quantum fluctuations or 0-point motion of these spins. And as we tune it at 0 temperature, the system undergoes a transition from an ordered phase to a disordered phase. Okay, so this is the t=0 phase diagram. This is the ground state phase diagram. There's only one axis here, which is this parameter called the transverse field. And as we tune it, the system undergoes a continuous transition at some critical value from the ordered phase, where these Ising spins are all aligned, to an Ising disordered phase, where they're pointed in a random direction. Okay, now, of course, real systems are never at 0 temperature. So you can ask, what does this have to do? How do we actually measure the properties of such a quantum phase transition?
This is Ising or Heisenberg model?
This is so this particular case is an Ising model, and you can ask, what do I mean by having them at an angle? Right. So if I really measured them along the Ising axis, I would get, of course, up or down. Okay. So yeah, this picture maybe is a little bit misleading. There's also a version of this model that you can write for Heisenberg.
Why is this a continuous transition? It can't be a discontinuous one.
So it can be. It can be. So in the simplest transverse field Ising model on a square lattice in 1 or 2 dimensions, it turns out to be continuous, but that's never guaranteed. Okay, that can actually depend on microscopic details. Okay, but right, but some transitions at least can be continuous, and I'll discuss these in particular here. Okay. All right. So yeah, so how do we actually probe the properties of such a transition that theoretically should occur at 0 temperature, but we of course never reach 0 temperature? Okay, so it turns out that if you add to this axis, to this phase diagram temperature, there would be a broad region in phase space called the quantum critical region, whose properties actually reflect the properties of the underlying quantum critical point. Okay, so you can think about this region as follows. So temperature provides a cutoff or a length scale to the system, where if you tune the system to the critical point, it lacked any intrinsic length scale because the correlation length diverged. Temperature provides such a length scale, such a cutoff, and now all the properties of the system, such as susceptibilities, correlation functions, and so on, would depend on temperature in a way that reflects the scaling properties of the underlying quantum critical point. Okay, so this quantum critical regime and the scaling behavior that occurs here is what one would typically look for in real life. Okay, so how do we analyze such quantum critical phenomena? So it turns out that there's a very, very powerful tool to do that. And here, indeed, I'm illustrating it using a more Heisenberg type spin model. Okay, and this is called the classical to quantum mapping. Okay, and that's a very, very useful tool to think about quantum many-body problems in general, and these types of problems in particular. So it turns out that you can always map a d-dimensional quantum system into a d+1 dimensional classical equivalent problem. Okay, and the extra axis that appears in the equivalent classical problem is called a Euclidean time, or a imaginary time. Okay, so it's like an extra axis in which your degrees of freedom or spins can also fluctuate, just in the same way that they can fluctuate spatially. And the size of this extra dimension is basically inversely proportional to temperature. Okay, so in the limit of 0 temperature, it diverges and it really behaves like an extra dimension that your system lives in. Okay, so that means that in many cases, if you want to know the properties of the classical critical point, all you need to do is just increase the dimension by 1, add this extra Euclidean time, and then go to your favorite StatMath book and just read off the properties of the corresponding classical critical point in one dimension higher. Okay, so yeah.
It's not always a plus 1. It depends on the
right. So yeah. So right. So now there are differences. Okay. So what Efrat is saying, okay, this extra dimension is not always equivalent or related. Of course, it's different from the spatial dimensions. Sometimes it behaves. The system has an emergent symmetry that relates space and time, Lorentz symmetry, and sometimes it doesn't. Okay. So yeah.
We have a two-dimensional quantumizing system that allows for effect quantum phase transition.
Right.
Is that equivalent to a three-dimensional infinite temperature? It will be equivalent to three-dimensional Ising model?
Zero temperature. Yeah. Yeah. Right. So yes, that's exactly right. So if you have a two-dimensional quantumizing model, and it's important that it's quantum, so meaning it has a transverse field, different terms don't commute. So, and you go to zero temperature, okay, and you look at the critical point between the ordered and disordered phases. The claim is that you can read off the critical exponents, okay, say the power law in which the correlation functions would fall off as a function of space or as a function of imaginary time. They would be exactly the same as the classical 3D Ising model, okay, which has a thermal transition. So that's exactly the statement. And as Efrat says, this trick works beautifully in some cases where the system actually has an emergent symmetry that relates space and time, okay, which of course is not a symmetry of the original problem. That's again one of these emergent symmetries that tend to appear at critical points, but don't always appear. Now I'm actually going to discuss cases where they don't appear. Okay, so sometimes, for instance, part of the richness, the reason why quantum critical phenomena are not the same as classical phenomena, sometimes when you have the emergent scale invariance, you have to rescale space differently from the way you rescale time. That's what Efrat was referring to. Okay, this is called dynamical critical.
Can you clarify what is the temperature in the classical limit? What's the corresponding temperature?
Right. So the corresponding temperature has nothing to do with the physical temperature, of course. Okay, it has to do with the strength of the quantum fluctuations. Okay, because what tunes the transition, what tunes through the transition in the quantum problem is the strength of the zero-point motion. Okay, how light your particles are, or in the transverse field Ising model, the ratio between the transverse field and the exchange couple. Okay, so that would translate at the end into the temperature parameter in the classical problem.
I'm not sure that I fully understand. I want to go back to Efrat's question. Does it have to be exactly an extra one dimension? Or can you think of systems that should be more than a single dimension, extra dimension?
Right. Yeah. So so there are all kinds of cases. In the simplest case, say in the Ising model or quantum Heisenberg model, it is just like an extra dimension. Okay. So it literally, from the critical phenomena point of view, it literally behaves like an extra dimension. In some cases, it behaves like an extra dimension, but this extra dimension is not equivalent to the spatial dimensions, even at the long wavelength limit. Okay, so it's like a higher dimensional system, but very, very strongly anisotropic higher dimensional system. Okay, so these are typical cases. Now there are cases where you actually need to think about more dimensions, but yeah.
Can it take place in a finite temperature? This mapping?
Right, so that's very interesting. The mapping works at any temperature. Okay, and that's actually very interesting on its own. So you see what happens. If you try to do this at finite physical temperature, the mapping still works, but you map the system into a system which is infinite in the spatial dimension, but finite in the temporal dimension. It's like a slab. Okay, so you need to think about the statistical mechanics of this kind of a system, which is in the thermodynamic limit only in in all the dimensions except for one. Okay, so it's an infinite slab, and it turns out that at the very longest length scales, the system would always behave classically, meaning it would always behave like a d-dimensional classical system. Okay, so in this sense, the quantum problem is very, very special. It's only its properties are only revealed at zero temperature, or in the temperature going to zero limit. Okay, yeah. Any other questions, comments?
Yeah, so this has to break somewhere, because when the temperature becomes too high, in order to be larger than the quantum fluctuations, so
yes, yeah, absolutely. So what an experimentalist does, right? So they cool towards the critical point and hope to see the scaling with temperature. Okay, and that reflects the properties, the scaling properties of the underlying critical point, and this would only work as long as the temperature is low enough compared to some cutoff scale where these fluctuations form. Okay, so yeah, this would work below some energy scale, some temperature scale. Okay, in the same way that in usual critical phenomena, you need the correlation length to be long enough in order to start seeing properties of the nearby critical point. Okay, the same idea. Yeah.
So like you keep saying that you can map the system to T+1 dimensional system, and you keep saying that it's T+1 dimensional classical system. But like if I would have very phase effect, for example.
Excellent question. Okay. So yeah. So right. So absolutely. This picture is way too simplified. It sort of implies that quantum and classical are the same. Of course, they're not. And one important difference is exactly that, and I'm going to talk about. Yeah. So the question was, what about systems that have very phases? Okay. There, I can. Yeah. So what I can always do is map my quantum problem into a problem of a big sum over numbers. Okay. No operators, no non-commuting operators. Formally, the problem looks classical in the sense that I can write my partition function as a sum over some a configuration space. But the price I'll have to pay, exactly as you say, is that some of these weights in this sum in the partition function would be complex. Okay, I have no guarantee that they would be probabilities, classical probabilities. That's exactly the point of this talk. Okay, so yeah. All right, yeah, great. Any other questions or comments? Yeah, this is. All right, so yeah, so now I'm going to switch gears, okay, and talk about a very intrinsically quantum mechanical problem, which indeed you struggle to do this mapping on. Okay, so this mapping doesn't go as smoothly. It always goes through formally, okay, in the sense that you can always write your partition function as a classical looking sum, but all kinds of things start going wrong. Okay, so I'm going to talk about metals. And metals are characterized by the presence of a Fermi surface. Okay, so as we know, in a metal, you have this sharp surface in momentum space that separates the filled states from the empty states, and the elementary excitations of the metal are these objects called quasi particles. Okay, so these are point-like objects, basically electrons you can add on top of the Fermi sea in the empty states, and they interact with the Fermi sea and leave this long halo. Okay, so these are the quasi particles of the metal. Okay, so here's what it looks like in a typical material. Okay, so there's a Brillouin zone, Kx and Ky. I'll be thinking about 2D metals in this talk. And here's our Fermi surface, and you can add either quasi particles or quasi holes as the elementary excitations of the system. And the interesting thing is that this Fermi surface is intrinsically a quantum mechanical object. Okay, there's no classical analog. There's sort of an intrinsic length scale in the problem, which is the Fermi length scale, Fermi wave vector, which has no classical analog to it. Okay, and moreover, the elementary excitations of the system live in the surface in a momentum space rather than at the point. These are all things that are very uncharacteristic in a classical problem and are kind of appear here very naturally. Okay, and the question I'd like to ask is, let's tune the quantum fluctuations in our system, just like we did in the quantumizing model, using some parameter, and tune our system to just to the verge of an instability towards forming some kind of ordered state. Okay, so this is what we might expect to happen. The fluctuations of the incipient order parameter would be so strong, and it would scatter the quasi particles and quasi holes so strongly that they would actually lose their identity. Okay, so if they scatter a lot, they stop being eigenstates basically. Okay, and the Fermi surface might become smeared. Okay, so rather than a discontinuity in K-space, we might get a much weaker singularity. Okay, so this is called a critical Fermi surface. So this is what the distribution of particles in momentum space might look like at the ground state, right at the verge of this instability. And the question is, how do we analyze this type of problem? Basically, a metal just on the verge of becoming unstable. Okay, so just to show you that this has something to do with real materials. Okay, and this is a big part of why this problem has been so intensely studied over the years. Okay, so there seems to be an intimate connection between quantum criticality in metals and unconventional superconductivity. Okay, so here's, for instance, a phase diagram of a material. This is a heavy fermion material. Okay, so there are two tuning knobs here. One of them is pressure. Okay, that's a non-thermal parameter that you can tune in theoretically even at 0 temperature. And the other one is temperature. And what you see here is that in some range of pressure, the ground state is an antiferromagnet. Okay, the spins order antiferromagnetically. And as you tune pressure, in the L temperature, where this antiferromagnetic order appears, drops to 0. This is tuning the metal to the verge of an instability. And instead of remaining metallic, there is this region in the phase diagram where instead the system actually becomes superconducting. And moreover, the highest DC is close to where the critical pressure is. Okay, so this is one specific material. Here's an organic superconductor, again tuned by pressure. And the details are different. STW means spin density wave. That's notionally the same as an antiferromagnet. It's some periodic ordering of the spins in this material. And again, the quantum critical point where the ground state becomes unstable towards antiferromagnetism is covered by this superconducting phase. Okay, this is a cuprate material, again, antiferromagnetism and superconductivity. And this is an iron-based material. Okay, so these materials are vastly different microscopically. Okay, the quantum chemistry of these materials is as different as it can be, but nevertheless, you see the same topology of the phase diagram everywhere. Okay, so this at least suggests that there's something universal or detail insensitive that is going on in these materials. Okay, and the appearance of unconventional superconductivity again and again in different systems appears right at the border where the metal becomes unstable to forming some kind of ordered state. Very often antiferromagnetic order, but not always. Okay, and there's another thing I'd like to draw your attention to. Okay, so in this phase diagram, there are colors. So what do these colors mean? Okay, so this is a log derivative of the resistivity of the material as a function of temperature, going up or down in temperature at the fixed composition. X is the composition of this material. Okay, and we know that in a normal metal, due to electron-electron interactions, what we get is that the resistivity scales like temperature squared. Okay, this is a well-known property of Fermi liquids, and this is indeed what we seem to find in either side of this instability. Okay, this blue color here means rho goes like T squared. Okay, so this is associated with Fermi liquid behavior, but you see this sort of fan-shaped region, which is colored red. Okay, that corresponds to rho goes like T. goes, the resistivity of the material scales linearly with the temperature. This is again something that's very characteristic of these quantum critical regions of metals. You find this in many different materials, and this is people interpret this as a breakdown of Fermi liquid behavior. This is exactly the property of a Fermi surface that becomes blurred. It loses its identity and behaves qualitatively differently from a Fermi liquid. Yeah.
Blue is still far from black is more like.
Yeah. So it's actually changing gradually. The exponent you will extract is changing gradually.
And it is,
right. I mean, the real statement is that in a Fermi liquid, at low enough temperature, it should be T squared. Now, of course, at high temperature, you can get all sorts of crossovers. Okay, but yeah, but you're right.
And the last argument, so when they determine scaling, you need to have some, I don't know, range, yeah, to determine it accurately, because there is difference between all these forces, extremely small, depending, of course.
Yeah.
So what is the range when all these experimentally being determined and saying this is T and this is T square?
Yeah. So it varies hugely between system and system. So in the best linear in T that people report can have 2 orders of magnitude, not more. Okay, in temperature.
Before pollen starts picking up.
Yeah, so right, exactly. All sorts of things go wrong, right? When you go too high, and you can't cool too low. Yeah, so this is not never at the standard of critical phenomena in helium or something. Okay, where you can really measure critical exponents over many decades.
Because people repeat this argument all over again about time being T and T square, and it's always being.
It's not always at the standard level. Yeah, I totally agree. Yeah, that's right. But how good it is really varies by system, and you need to be really careful. Yeah.
Just a comment. So in all these examples, the unconventional metal is not at 0. It's a finite temperature.
Yeah, absolutely. So so I've been talking about what happens to the Fermi surface at 0 temperature, where it has a chance to be well defined when you tune the system to the verge of the instability. Well, it turns out that often what happens is that the Fermi surface doesn't even exist at 0 temperature. Okay, and the actual critical point, there is a critical point, doesn't occur in a metal. It actually occurs in a superconductor. Okay, so that's one possible answer. Okay, what is the property of quantum critical Fermi surfaces? The property is that they don't exist. They actually disappear. Okay, so nature seems to favor that. Now, in experiments, what people often do to reveal the properties of the quantum critical point, they try to destroy the superconductor in some way. Okay, so one very effective way to do it is just to apply a big magnetic field. Okay, so that's a way to reveal the underlying normal state that would have happened if you didn't have superconductivity. Of course, the magnetic field itself affects the system. Yeah. Okay, but I'll show you later our simulations. And unfortunately, in our simulations, we can't do that. We can't apply the magnetic field. And indeed, in almost all cases that we studied, we always find that the critical point is indeed covered by superconductivity. All right, so yeah.
The cuprate diagram is slightly different because of the pseudogap as well.
So here I've shown a electron doped cuprate where they called this a pseudogap. It's very different from what people mostly refer to as a pseudogap, which is in the other side in the whole doped regime. Okay, this is much more limited and much better understood pseudogap. Okay, so this phase diagram, I feel comfortable enough to include in this class. The one that most people focus on, the whole side, is much more complicated and I think much less well understood than this, even though, of course, even this is not completely well understood. Okay, but yeah, good comments. All right. So how am I doing with time? Probably not great.
There's 25 minutes at the yellow end.
Yeah. Okay. So I'll just describe briefly how one makes progress. Okay. So we'd like to try to make sense of all these phenomena. So here I'm going to be thinking about two types of quantum critical points. So the quantum critical phenomena always depends on the symmetry of the order parameter. One type of critical point is a critical point where the spatial symmetry of the system breaks down to a lower symmetry. Okay, so this is realized in some of these materials I've shown. You start from, say, a square lattice with a Fermi surface, and spontaneously at some point, the system likes to break the square symmetry into a rectangle. Okay, so it picks a direction, either X and Y. This is called an Ising nematic, an analogy to liquid crystals, okay, that break a rotational symmetry. It's Ising because it's discrete. We start from a square lattice. So in this type of order parameter, imagine the electrons, rather than flowing isotropically, prefer to flow along more easily along one of the two crystalline axes. And this picture illustrates what might happen to the Fermi surface in such a system. We start from a Fermi surface that respects the square lattice symmetry. And when you go to the ordered state, it actually distorts either along X or along Y. Okay, and there are points on the Fermi surface that actually stay put. Okay, so these are called cold spots because they couple most weakly with the order parameter. And the other type of quantum critical phenomena I'll consider is the anti-ferromagnetic quantum critical point, okay, where the spin moments of the electrons become spontaneously ordered in some finite wave vector, for instance, pi. Okay, this kind of checkerboard pattern shown here. Okay, now this type of ordering is characterized by a very different kinematics on the Fermi surface than the case of the Ising nematic. So here what happens, if you're very close to the critical point, the spins are going to fluctuate very strongly in this particular wave vector. Okay, and in two spatial dimensions, there's going to be a discrete set of points on the Fermi surface that can be scattered resonantly from a point on the Fermi surface and ending at the point on the Fermi surface. These points are going to couple very, very strongly to these fluctuations, critical fluctuations of the order parameter, and all the rest of the Fermi surface is going to be coupled much more weakly. Okay, so these are called hotspots, and this is where most of the action is going to take place. Okay, so as theorists, we try to write simplified models that capture the essence of these types of phenomena. And we rely on universality that tells us that if indeed we are close enough to a critical point, the microscopic properties of the system are going to be washed out. So we shouldn't try to actually model all these complicated materials microscopically, but we should just try to capture the essence of the degrees of freedom that participate in the long wavelength behavior, okay, or the low energy excitations of the system. And there's just two types of these excitations. There are the quasi particles, electrons and holes in the vicinity of the Fermi surface, and there are the fluctuations of the incipient order parameter. Okay, the long wavelength fluctuations of the spins or of these distortions, long wavelength distortions of our Fermi surface. Okay, and what we write basically is just a simple quantum field theory that describes these two types of degrees of freedom and the interactions between them. So I'm going to write a quantum action. Okay, so this quantum action has three terms in it. The first term describes the fermions, and for simplicity, we'll just treat these fermions as free fermions forming some Fermi surface. This spin. Yeah, so depending on the problem, we can consider a spin-full or spinless electrons. Okay, so of course, in real life, they would be spin-full. They might have different orbital indices and so forth. I didn't mention that explicitly here. Okay. The second term, this S phi, is the action of these fluctulations of the order parameter phi. Okay, so phi would be a bosonic field. Okay, so it's you can think about it as a field made of bilinear of these underlying electrons. And for that, we just write the usual expansion in powers of phi. So the order parameter near the critical point is small, so we can expand the action in powers of phi. And it's very slowly varying in space and time, so we can also expand in the gradients of this field. Okay, so that's the usual Landau type of expansion. And finally, we need the interaction term that couples these two types of degrees of freedom. Okay, and the lowest order interaction you can write is this Yukawa type term, okay, which is linear in the bosonic field and quadratic in the fermions. And again, there might be higher order terms, but these would be less important close to the critical point. The lowest order term is always the most important. Okay, and that's it. That's our theory. There are all kinds of details here that depend on the precise type of critical point we're considering. For instance, in the case of an antiferromagnet, this phi would be the order parameter of an antiferromagnet. That will be a vector, and it couples to the spin of these electrons, not to their density and so forth. I've sort of, I didn't write all these things explicitly. The type of coupling here depends on the symmetry of the order parameter. But schematically, this would always be the type of action that we expect to capture the properties of the system close to this critical point. Okay, so it's just a problem in quantum field theory. That's all it is. It turns out to be a hard problem in quantum field theory, not one that you'll find in your typical quantum field theory book. And this is why people are still debating this problem. So in quantum field theory terms, you would say this Yukawa coupling is a relevant parameter. Okay, so it really modifies the properties of the system, at least in two spatial dimensions, which is a relevant dimension for many of these materials. It actually completely modifies the properties of the system at low energy scales. And this is what makes it hard. Okay, under RG, this coupling flows to strong coupling, and there's no nearly free description. Okay, so these are some of the things we'd like to know about this theory. Okay, critical exponents, what happens to the Fermi surface? Is the system becoming unstable to superconductivity, for instance? Does this model really capture this tendency of critical metals to go superconducting or not? Okay, let me just mention some piece of physics here, which is interesting. Okay, these bosonic fluctuations near the critical point actually play a dual role, and this competition is really the key here. Okay, so what do they do? First of all, they scatter the fermions like mad. Okay, so you have these very, very soft modes. Fermions scatter often very, very efficiently. And this leads to the breakdown of Fermi liquid and a breakdown of the coherence of single quasi-particle excitations. So this loss of coherence is one strong effect. The other effect these fluctuations are playing is analogous to the role of phonons in a BCS superconductor. Okay, so whenever you have electrons interacting with the bosonic mode, this bosonic mode mediates attraction between electrons. And if this bosonic mode is very soft, this attraction is very strong. Okay, so there's a very strong tendency to these quasi-particles to also pair together. Okay, so these two effects are competing. On one hand, these quasi-particles scatter and lose their coherence. On the other hand, they try to bind into coherent Cooper pairs. And it's really this competition which is the key here. So this competition sort of captured in these two proposed phase diagrams from paper David Ross and Max Matlitsky. Okay, one possibility is that superconductivity wins. You go straight from a state of coherent electrons with the Fermi surface into a superconductor that washes out the quantum critical regime altogether. The other possibility is that you have this very wide, broad region of a critical metal, non-Fermi liquid metal, and superconductivity only emerges at very low temperature out of that. Okay, so which of these two, if at all, is actually realized? Okay, so this problem is difficult in two spatial dimensions. It's a problem that people struggle with for a long time. I think recently there's starting to be very interesting progress, but in many cases we still don't know the answer.
Can you clarify for me a simple point? I mean, at the beginning you said you're going to turn this into a classical problem.
Yeah.
So it's not a 2D anymore, it's a 3D plus
it's
one.
It's a 3D, yeah, it's a 2 plus 1.
What you're
3D.
doing here is the classical problem essentially.
Yeah, so right, so yes, excellent. So what I can do for you always, I can write the partition function corresponding to this model as a classical sum over amplitudes. Okay, so there's no non-commuting operators. In that sense, it's classical. Okay, of a partition function that lives in 2 plus 1 in three dimensions, 2 space plus 1 time. Okay, that I can always do. What I can guarantee is that the terms of this sum would be real positive numbers. Okay, so in that sense, it's not really a classical StatMech problem. Okay, in a classical statistical mechanical problem, the terms in the Gibbs sum are probabilities. Okay, so this doesn't work usually here. Okay, the miracle is, that's actually the point, and maybe with that I'll finish. The miracle here is that in many of these systems, in many of these problems, there's a symmetry that guarantees that all the terms in the sum are actually real and non-negative. Okay, and then this mapping really works, and you can really treat it as a classical statistical mechanical problem in one dimension higher. It would be a weird problem. It's very non-local. Okay, it's not the usual one you find in the StatMech books, but at least you can treat it numerically in a computer. Okay, so yeah, so that is indeed the point. Okay, our approach to this problem is it's called quantum Monte Carlo, and that relies exactly on this mapping, classical to quantum to classical mapping. We map our problem into an equivalent D+1 dimensional problem, and we can do this in this case. Okay, we start from a model of fermions. Fermions have no classical analog, but we can integrate out the fermions. Okay, so in technical terms, the action is quadratic in the fermionic degrees of freedom. We can always integrate them out and introduce some effective action of this field phi alone. Okay, so our action is going to be written entirely in terms of this bosonic field phi, and that we can treat as a C number. Okay, so we have some partition function, which is a sum over configurations of phi with some effective action of this field phi. Yeah.
So do these quantum fluctuations have to be bosonic? I mean, what makes them bosonic? Yeah,
right. So it turns out that an order parameter can never be a fermion operator. Okay, a fermion can never order. So a fermion is not observable. It would never condense in technical terms. Okay, that's actually a theorem. So yeah, so now you can ask, what do we do with problems where we cannot write the order parameter as this kind of local field? That's a very good question. Not all critical phenomena are characterized by this kind of local bosonic order parameter. That's also true. I'll only be treating the class where you can. Okay. So, yeah. So now, unfortunately, okay, this effective action in general would actually be a complex number. Okay, and this is actually no big surprise. We started from a problem of fermions. We know that fermions have fermionic exchange statistics. So this property of fermions comes back and haunts us even after we integrate out the fermions typically. Okay, so this is a complex number, meaning that we cannot use just stochastic sampling to get properties of the system by doing a random walk in configuration space. Okay, because these are not probabilities; these are complex numbers. So this is the infamous sign problem. Now it sounds like a very technical problem, but it turns out that it's not. Okay, so this is actually a very deep and fundamental problem. In some sense, this is the difference between classical and quantum. This is where it's hidden. Okay, and you can sort of brute force your way treating this problem still as a classical problem. For instance, sampling according to the absolute value of these quantum amplitudes, and then reweighting the complex phases when you measure observables. But it turns out that the problem would remain exponentially hard in the system size, just as any quantum many-body problem. Okay, so this problem really has deep roots. Okay, in some sense, you would say if this wasn't the case, quantum computers wouldn't be any stronger than classical computers. Okay, for a general problem. So this is really a fundamental problem. Now, luckily, in the problem at hand, it turns out that in many relevant cases, not all, but in many relevant cases, there's a symmetry in the problem that actually guarantees that after integrating out the fermions, the resulting effective action is a real non-negative number. Okay, and I won't go into technical details, but this was the key to this advance. Okay, so you can either take the original problem, integrate out the fermions, and just prove mathematically that the resulting action is a real non-negative number, Or you can modify the problem slightly in a way that we believe doesn't change the universal properties, and that problem has that symmetry that we look for. Okay? And I won't go into details, but this actually at least allows you to make progress on a computer. Okay, so if this effective action is a real positive number, let's just treat it as a probability, and just and then we have very effective methods to actually draw configurations of phi from this distribution. We basically treat this as a probability distribution, and then we can compute any property of the system that you like, okay, at 0 temperature or finite temperature. Okay, so yeah, so I'll just maybe just say a few results that we accumulated over the years of this very broad class of problems, and with that we'll conclude. Okay, so first thing we'd like to know, okay, are these systems really superconducting close to the quantum critical point? Okay, we tune the system to the verge of criticality. What happens? Is there superconductivity? Yes, there definitely is. Okay, so it turns out that these are two very different models that realize different types of critical points in metallic systems. Okay, of course, yeah, these are almost literally the types of we start from the type of model that I've written before. Electrons coupled to some bosonic field, interacting by this Yukawa term, and we tune some parameter in our Hamiltonian that tunes us to a critical point. Luckily, in these systems, it turns out that the transition is continuous. This didn't have to be the case. It could have been first order. But in both cases, you see that the critical point where the order, whatever that order is tuned close to 0. The critical point is actually covered by a superconducting phase. Okay, so that superconductor can be S wave or D wave, depending on the problem, but it's always there. And it seems to be strongest close to where the critical point is. Okay, next, we'd like to know, are there any other types of competing order that occur? So we see that close to the critical point, the system tends to become unstable and become a superconductor. What people proposed, motivated by the fact that in many of these materials, there are many different competing types of order. People propose that there are other candidate orders that can also appear, spin density waves, charge density waves, that all compete in the vicinity of the quantum critical point. So we looked for that and we couldn't find it. Okay, so it turns out that the only robust order that you get in the vicinity of the critical point in these models is superconductivity. Another very appealing idea was that the so-called pseudogap phenomenon, namely a big gap that opens up for the fermions close to the Fermi surface in a broad range of the phase diagram, is also tied to the vicinity of the critical point, and we couldn't really find that either. Okay, so there is a gap that opens before you actually hit the superconducting phase, but it's sort of confined to a narrow region above the superconducting PC. Okay, so how do you describe the quantum critical region? There's this quantum critical fan kind of fanning out of the critical point. At weak coupling, nothing much is happening there. Weak coupling means a weak interaction constant between our critical fluctuations and the fermions. But when you crank this coupling to be considerable, it turns out that there's a broad regime where indeed the system seems to deviate from Fermi liquid behavior. Okay, so above TC, up to a very high temperature, the system behaves like some kind of anomalous or non-Fermi liquid metal that we're still trying to characterize.
Sorry, question. Yeah. So when you say weak coupling and strong coupling, there is certain coupling that you need to have to go through the critical point.
Right. So actually not in these models. The way these models are designed is that there's a bosonic part of the action, fermionic part, and coupling between them. The bosonic part by itself would realize the critical point. Okay, so this is an artificial thing. Of course, in real life, you don't have that. Yeah, I can decouple them if I want. Yeah, and the first thing that we see, by the way, if we didn't have this coupling, the transition would actually occur here. Okay, it always gets pushed. It's the coupling to the fermions stabilizes the ordered phase. Okay, so yeah, so this is a very useful parameter, both conceptually and actually numerically. Okay. Yeah. Okay, so yeah, I'm basically done. So I'll just summarize. Okay, so the properties of many of these quantum critical metals are now accessible using a numerically exact Monte Carlo simulations, and we've done some simulations. Okay, it looks like the quantum critical point is generically hidden underneath a superconductor, which is mediated by the quantum critical fluctuations. There are interesting properties of the critical state above DC. Okay, now, unfortunately, unlike in the experiments, we cannot apply a magnetic field and suppress the superconductor. It turns out that that very generically causes a sign problem. Okay, and it looks like actually the fact that the zero temperature metallic state is covered by a superconductor is no accident. Okay, we now believe it's something fundamental. It's a model which is free of the sign problem can never actually realize the Fermi surface. That's something we're trying to understand better. Empirically, at least, that seems to be the case. Okay, but we are modeling, if you like, the zero magnetic field phase diagram only. Okay, and there's some interesting features of real materials that seem to be missing in these class of models. People were optimistic that maybe they would just pop out, but they seem not to. Okay, thanks very much.
Thank you. Yeah, questions?
So, I mean, is there any physics in this story of the sign problem? I mean, is there any fundamental? Isn't there any fundamental physical difference between systems, quantum systems, in which you have the sign problem,
yeah,
or in which you don't have?
Yeah,
I mean,
yeah,
it's not only appears to be not only a computational issue, but a physical issue.
Yeah, yeah. So I believe there is. So what people have been realizing gradually is that it's not just a property of the Hamiltonian. It's really a property of the phase you're trying to describe, or the ground state that comes out of that Hamiltonian. So you can ask the question: what kind of phases of matter are describable using in a sign problem-free setting, and which don't? And there's starting to be theorems saying certain phases of matter just cannot be realized no matter what you do in a sign-free problem. So indeed, it seems to be tied to the physics. It's not some technical problem, but I think there's much to be clarified there. Yeah, I mean, it has to do, yeah, I mean, intuitively, if the low energy excitations of the system have some non-trivial statistics, for instance, you would expect never to be able to describe the model using a sign-free model, no matter what microscopic degrees of freedom you start from.
So you introduce at least a weak magnetic field by using the traditional tricks for sign prop.
Yeah.
And
yeah.
Just understand and see what's happening with
right. Yeah. So that's a good question. So even when there is a sign problem, sometimes there's such a thing as a weak sign problem. Like you would say, the sign problem really means that the problem becomes exponentially hard with system size. But there's a question of the coefficient of the exponent, right? We always do our simulations in finite systems anyway. The question is, can you get away with it? So far, we've not really tried to go that road. Okay, there were enough things to do with the sign-free problems, but that's definitely an interesting thing to try.
Any additional questions?
So is there any unique footprint of the sign problem in the entanglement of the ground state?
Yeah, good question. I mean, yeah, there should be, but I don't know any concrete results about that. Yeah, so you know, I mean, systems can be strongly entangled and still be sign-free, or vice versa. Yeah, I mean, you know, we believe Fermi surfaces cannot be described. It's just a Fermi liquid, so unlike Fermi gas. So interacting fermions that form a sign problem, that form a Fermi surface cannot be described probably by a sign-free model. That has an anomalously high entanglement associated with the Fermi surface. But I don't know how to make that more precise.
Yeah.
Well, so if I would try to do a renormalization group in a particular way for these systems, I would well, like we wouldn't integrate out Fermi because if you need to integrate divergences here, you integrated for numerically integrated them out without sort of like pair of
So it's a very good question. This is something that's not advisable to do, exactly as you say. As a result of integrating out the fermions from the outset, what you get is a problem which is very non-local in space and time. Okay, so our effective action is actually extremely non-local. This is what makes it, okay, this is where the remnant of the Fermi surface actually is. Okay, this is what knows about the presence of the Fermi surface. But we treat the problem numerically, so we don't, it makes the problem more difficult numerically, but still manageable.
Can you suggest a recipe or some idea how to design scientific models?
So, so it turns out, we've actually followed a very nice recipe, exactly such recipe. From Conjun Wu. What he pointed out is that what you need is a form of time reversal symmetry. Now, the physical time reversal symmetry is not enough. What you need is the effective action in every space-time configuration, the action matrix of the fermions, to be time reversal symmetric. Okay, which is a much stronger condition than having the physical time reversal. Okay, so that comes with the Cramer's theorem, and that's why there's no sign problem. Every eigenvalue of that matrix must come with its complex conjugate. Okay, so that was one sort of design principle. And since then, actually in recent years, there are several other sort of design principles were discovered, and all relying on some symmetry of this action matrix, of the space-time action matrix, and we're trying to understand the physical properties. So, given that you have that symmetry, what does that imply on the physics? Okay, and this is how we approach the problem of what's the physical content of the sign problem.
Okay, so we're out of time. Let's thank Gareth again.